D is proportional and D is derivative. So one example is like this. So here is our open system, 1 square. So this one simply represent is only a mass, okay, a mass block. So if you remember in our spring, this is only pure mass. The pure mass is the force equal to ma, right, equal to mx double dot. So once we take the Laplace transform, basically it's force equal to n times s x squared. So basically here that means the this is force and this is the x. So basically x equal to f divided by n and times 1 over s squared. So that means here we in the physical system, basically representing is a pure mass. Okay? Because sometimes when we are dealing with a system, by looking at the system, right now I believe you should have the certain feeling or knowledge you can right away to identify what is the feature of that system is. Okay, you must have that kind of capability before doing the detailed calculations. Okay, so right now we have this one. So this is basically is a controlled open loop of a pure mass and without anything. So if we want to change the dynamics, and basically here we can feedback is we simply added up a proportional control, and then we call that P, and also we added up a derivative control, or we call the speed control. Basically this is adding a certain, for example, that is equivalent to add the damping, the viscous damping, okay? And this one simply is to add it up certain spring, negative spring feedback here. So basically here we put into the feedback here is something like this one, okay? So for this case, the closed loop system, so right now let me modify in terms of our symbols, the symbol we've been familiar with. So y over r will be equal to, let me call this is g, let me call this is h, will be g, and 1 plus gh. Okay, so that is the closed loop system. So here the characteristic equation is simply is 1 plus gh equal to 0. And based upon that one, we're going to plot the roots. Okay, so here basically we're plugging here g equal to 1 squared and h equal to p plus ds. Okay, so let me revise this one, 1 plus. And right now you can see here we have two parameters. Here we have two parameters, and what we have learned in plotting the root loci is we're only dealing with one parameter k. So how can we utilize our root loci techniques to deal with this one? Here I can introduce you a simple technique. We can do this. Let me modify this one first, okay? And p plus ds, okay? And so I'm going to modify is this. The strategy is this, because here with two parameters, I want to utilize the root loci technique. So I'm going to try is this 1 plus p over d. So I simply divide the whole things by d. So p over d plus s, and so here I simply turn the numerator, the d from the numerator out here, okay? So here is s, here is d. So the strategy you can see right now, D is in this kind of placement. D plays a role as K, right? So that is our unknown. So in our strategy is this: at every single trial, I keep P over D as a constant, a certain constant that I define. So here, my strategy is this, keep the ratio of P over D, say, for example, equal to 1, then I study the behavior of the corresponding root loci. Then if I couldn't find the appropriate behavior of the system I want, then I simply change this ratio and then redo the analysis again. Okay, so the strategy is to this, keep the PD constant for each analysis. Okay, so under these situations, then we can try. For example, the first try is simply D and 1 plus S squared equal to 0. So right now for this case, when P over D equal to 1, so that is scenario we study. Okay, so from here we can see and plotting the real and imaginary axis. So for this case we have two repeated poles here, and then s equal to -1 as zeros. So the corresponding root loci will be something like this. So that is something like this. Okay, so again, you can detail the drawing by calculating the breaking point here. Okay, if really necessary, then we can do the detailed calculations. Okay. So that's the one. So from here, we can repeat our selections. So for example, here, this is corresponding to D equal to 0. And from here, the D equal to infinity. So again, repeating our previous calculation. For example, you can select this point here. And for this point, say this is spatial value of the S bar. That is corresponding. So say, for example, equal to minus A plus JB. And here A and B can be calculated precisely. Okay. So the AB here is a precise number, so that means from there you should be able to calculate omega n and magnitude equal to A squared plus B squared. And this is the cosine zeta. Okay. So from here you can determine omega n and zeta, and that one can be determined. You good? So once omega n and zeta is determined, then you can also determine what is the corresponding D star value. Also determine D equal to D star at this particular point. Okay. So from there you determine the D star, and that is the value of the D. So once you have D, then you know the P. So that is one complete analysis. For this analysis, if you say I don't like the system behavior, so the system behavior basically is determined by the Q values. You have a damped natural frequencies, you have a damping ratio. So in the time domain, you can quickly, using our previous techniques, you can see, okay, that is the system behavior will be like this. For this case, it takes 10 seconds to forming into, say, the 5% stability criteria. Okay, so for example, let's say the system takes, say, 10 seconds. And for engineer, you feel that takes too long. I want to change it. I want, for example, this one can be shortened as 5 seconds. Then you simply keep playing. What would be the good numbers of the two? Keep playing to satisfy all the things. And how to make that keep playing? Basically, you simply keep selecting the different locations of those points on the root loci. Okay, and then every time you do the calculation, or simply using a MATLAB, you put your cursors roughly to there, and from that cursor, you know the window can give you the good numbers, right? From the cursor, you know the location of the A and B. So from there, also from cursor, you can get the number of the D. But again, the cursor really depends on how precisely you locate. And once you have that kind of the rough number, then you can proceed the detailed calculations. Good? Okay. For this scenario, if you wouldn't be able to find the satisfied dynamics, then what happened? Then you simply change this one, say for example to 2.5, and just make up one number. Under that new scenario, you would have a different root loci, right? So under that situation, this one will be s equal to minus 2.5. Then that's a different drawing. Then that will give you a different set of, I would say, selections. Keep doing. And using MATLAB, this one, if you write a simple program, this one can give you a lot of the calculation at a short of time. Okay, but for the beginning, you can just, for example, every time when I design the homework, this weekend I spent a half day to design the homework for the next chapters. I didn't write a program. I simply open up the MATLAB and doing the manually, if I do this on the scratch paper, and then I simply shift to and then write out something and waiting for the result. Once everything is determined, then I simply copy those codes into the M script, the M file, the script file, then from there that form routine calculation procedures. That's what I did. You good? Okay. So that is for this one. And here we have, and we can come up with a new section.